Alright everybody, so for this homework assignment I wanted to talk for a few minutes about what are called feedback loops. So if you remember from the lectures that we've had on climate change so far, and if you haven't seen them yet, well, come to class today and you will see them. But one of the things that you may have noticed at times was that climate change can actually be very sudden. Well, one of the main reasons why climate change can be so sudden at times has a lot to do with what are called feedback loops. And so for this week's homework, I'm going to have you investigate a few feedback loops, and the idea is really just to reinforce this concept of a feedback. So first off, let's actually talk about, in nature, what a feedback is. So a feedback is actually a response, a natural response, to an initial disturbance. So something stimulates nature, something disturbs the situation. So if you remember when we talked about stability, we had that ball on top of a hill, and then it was kicked. Well, the same idea is here. Or that's the same idea here. Like an initial disturbance, something throws the system out of its natural equilibrium. And in a climate system, this can include things such as warming or cooling, changing the atmosphere's composition, or even a change in the land-ocean distribution, and so on and so forth. So there are many different potential disturbances that could trigger a feedback. Now, once the feedback is triggered, there's one of two types of feedbacks. There are what are called positive feedbacks and negative feedbacks. Now, let me just be really careful here with the use of those words. Up to this point in your life, you've probably heard that, okay, positive means good, negative means bad, right? Well, that's actually not the case here when talking about natural feedbacks. Positive feedbacks aren't necessarily good. Negative feedbacks aren't necessarily bad. The only thing that really matters when talking about positive versus negative is how the natural system responds to that initial disturbance. In the case of a positive feedback, Mother Nature or a natural process will amplify the initial disturbance. So let's suppose that the initial disturbance was, I'll just say cooling, just to play devil's advocate here. Well, a natural system would then kick in to cause additional cooling. So in this case, cooling leads to additional cooling. Or warming leads to additional warming, and so on. A favorite example of mine, and no, you can't do this on your homework, since I'm saying it right here, is that, let's say I deposit money into a savings account. That's the initial disturbance. I have increased my balance in my savings account. Now, let's suppose that we live in a world where banks actually give you interest. Well, that savings account is going to collect interest. That's going to cause the account to grow further. And then that additional money will also eventually collect interest, which causes it to grow further and further and further. And for those of you who've ever watched Futurama before, eventually you end up like Philip J. Fry, where an initial deposit of 63 cents leads to billions and billions of dollars. The idea here is that if left undisturbed, or if left to its own device, an initial feedback or an initial disturbance would continue to amplify and amplify and amplify in a runaway cycle. It would just get more and more and more. Now, on the other hand, if you've ever woken up in the morning with a fever, believe it or not, a fever is actually a type of negative feedback. In a sense, your body is feeling the presence of pathogens, and the purpose of that fever is to actually get rid of those pathogens. Actually, a better example of this is us sweating. Our body temperature increases, that's the initial disturbance, and then our body triggers a response to cool us back down. In this case, that initial disturbance, the increase in body temperature, is counteracted by a natural process, us sweating, the sweat being evaporated, us cooling back down. In this case, the initial disturbance is eventually done away with. It is counteracted. It is removed back to normal. So for positive feedbacks, the initial disturbance is amplified. For negative feedbacks, it is counteracted. It is negated. It is taken away. And in case you're wondering, this is actually very similar to the whole stability-instability thing we talked about several weeks ago when we said that if you take a parcel of air and you push it up in the atmosphere, if it's unstable, it'll keep rising. That's a positive feedback. If it is stable, it'll just sink back down. That's a negative feedback. So, again, a positive feedback occurs when that initial change is reinforced by a natural process. These are unstable. On the other hand, a negative feedback, the initial change is counteracted by a natural process. This is like the ball in the valley. You kick the ball, it rolls up the valley, and it just rolls right back down. It's stability in this case. So again, this is an example of a negative feedback. Kick the ball, it rolls up the side of the valley, and then rolls right back down. And then this is a positive feedback. You kick the ball, it's just going to keep rolling and rolling and rolling. It's unstable. So what I wanted to do, without giving away too many of the answers from the homework, is walk you through a few important feedback loops. The biggest feedback loop that I want to walk you through is a positive feedback loop that accelerates a change. So that initial change is amplified. It's accelerated by nature, by some natural process. Now, these feedbacks can't initiate change. They can only alter the pace of it. So if you remember back when we looked at that graph of warming over periods of time, oftentimes you notice that warming was very sudden, or that cooling was very sudden. Well, here are a few key examples of this. The one I'm going to talk about is what's called the ice albedo feedback, but there are others, such as the water vapor feedback and the cloud feedback. These are all positive feedback mechanisms where an initial disturbance can actually lead to additional of that disturbance, can be amplified. But let me actually talk about this idea of what's called the ice albedo feedback. So this is actually going to be a homework problem. So I don't want to give the answers away too quickly, but let me walk you through just the initial part of it. So ice has a really high albedo. If you actually recall from very early in this course, ice has an albedo somewhere between 80, 85, 90%, sometimes even higher than that. It reflects most of the sunlight that hits it. Now, if we were to remove all the ice from our atmosphere, from the surface of our Earth, what would be left behind would have a much lower albedo. As a result, more sunlight would be absorbed, and the Earth would continue to heat up. Well, guess what? Ice melts. And since we know that our Earth is warming, guess what that's going to do to our ice coverage? Guess what that's going to do to the amount of ice on the surface of the Earth? As a result, since ice has a really high albedo, what is that going to do to the overall albedo of our Earth? And then finally, as the albedo changes, the less sunlight being reflected by the Earth means more sunlight is being absorbed by the Earth. So I don't want to go too in-depth into this again because this is actually one of the homework problems. But if you wanted answers, there they are. Hit pause, fill it in. The idea that I just want you to get, though, is that in this case, warming would be the initiating mechanism, which then leads to melting of ice. Since the Earth warms, ice melts. Well, remember, ice has a really high albedo. So guess what? By ice melting, that high albedo surface is being taken away. What's left under the ice has a lower albedo. So overall, Earth's albedo decreases. The amount of sunlight reflected by the Earth then decreases, and guess what that results in? That results in more sunlight being absorbed by the Earth. And think about this. If the Earth absorbs more sunlight, it's now absorbing more energy. That is going to lead to additional warming, which will then lead to additional decrease in ice coverage, which will then lead to additional decrease in albedo, which will then lead to additional absorption of sunlight, and so on and so forth. As long as there's ice on the Earth, this process could ideally continue until all the ice is gone. This is a type of positive feedback. Warming leads to more absorption of sunlight, which leads to additional warming. So, melting ice leads to more heating, which guess what? Leads to more melting ice, which then leads to more heating, which then leads to more melting of ice, and so on. Another positive feedback I'll talk about real quick, and now I'm going to give a cooling situation, has to deal with water vapor. So, let me just start by saying that water vapor is a very potent greenhouse gas. The more water vapor we have in the atmosphere, the more greenhouse gas we have in the atmosphere. So let's, now knowing that, let's discuss a situation where somehow, some way, Earth cools. Well, what would this actually do to the Earth? Well, if you remember, evaporation occurs when water gets hot. In a cooler Earth, we would have less evaporation. Now, we'd still have evaporation, but we'd have less of it. As a result, there would be less moisture in the atmosphere. And if you remember, water vapor is a key greenhouse gas. Well, now if we have less moisture in the atmosphere, that decreases our greenhouse effect, which then allows more heat to escape, further cooling our Earth, which then leads to additional evaporation, which then leads to additional decrease in moisture, which then leads to less evaporation, which then leads to less moisture, and so on. So that initial mechanism is then amplified. And in fact, there are instances where this happens as well. Take a moment and Google search snowball Earth. There's actually a theory that at one point, cooling was so run away. These feedback mechanisms that were cooling the Earth were so key or were so potent that the whole Earth was a snowball. Obviously, we're not that now. In fact, we're doing the other thing. We're warming a lot now. And if you want to see an example of runaway warming, look up Venus. Venus is an example of a runaway greenhouse effect. But again, cooling leads to more cooling. This too is a positive feedback. Now with that said, let me just take a few minutes and again, not giving away all the answers to the homework, I want to talk about negative feedbacks as well. Negative feedbacks are processes that reduce an initial change. So they take what initially happened and they negate it, they get rid of it, they delete it, per se. A good example of this is, again, if your body heats up, it sweats. That sweating then leads to evaporation, which cools your body off, and then, boom, your body temperature increasing results in eventually your body temperature decreasing. So that's just one example of a negative feedback. Again, you can't use that one in class because I've already talked about it. These trend towards stability. So the initial change is counteracted, and we go back to our nice, happy equilibrium. There are a few important examples. The one you're going to work on in this week's homework is what's called cloud feedback. There's also others, such as chemical weathering, which can then also counteract an initial change. But let's talk about this cloud feedback real quick. Before I go into it, again, let me just stress, positive and negative feedbacks have no relation to good versus bad. It's all just about how a system responds to the change. In the case of a positive feedback, the system amplifies the change. In the case of a negative feedback, the system reduces the change. So, here is a negative feedback. And I'm going to make you fill in the blanks. I'm not going to give you the answers because this is part of the homework. But let me at least get you started. So, let's suppose now our Earth warms. Okay? Our Earth warms. This results in additional evaporation. Now, as evaporation occurs and that water vapor rises in the air, it eventually expands, cools, and condenses, creating additional clouds. Now, with that said, clouds during the daytime are very reflective of sunlight. They're very reflective of sunlight. And can that cause cooling? On the other hand, at night, clouds do a really good job of trapping in radiation that the Earth is giving off. So, for the purpose of this homework assignment, you're going to ask the question, or you're going to answer the question, would additional clouds lead to cooling during the daytime or to warming during the daytime? And that's it. So, good luck on this homework assignment. Please feel free to reach out to me if you have questions, comments, concerns. But that's it. All right. Good luck, and thank you for watching.